Okay, yeah. So, good morning, everyone. So, let's begin lecture three. So, basically, in lecture three, I'll continue from where I left off about integrable models, and I'll just mention a certain thing quickly, which, of course, I also mentioned in passing in the last lecture. Uh, and then I'll go on to something which is much more recent and very exciting, which is this topic of many body quantum stars, which people are actively thinking of even now because there are several unanswered questions. And I'll give you a flavor of what's happening there. Okay, so that's the plan of today's lecture. And then hopefully by the start of tomorrow or lecture, or maybe, you know, after the first 15-20 minutes of tomorrow's lecture, I'll start talking about periodically driven systems and what are the new things in fluke physics which come up. Okay, so that's the rough plan for the rest of the thing. So before I begin, if there are some urgent questions from yesterday's lecture, please feel free to ask.
So,
Yeah.
probably this was also asked yesterday, and this might be a repetition, but still, when you are discussing this transversal Ising model, the growth of the entanglement entropy with time, that plot, when you were discussing that.
Mhm.
We are seeing that as you go to higher and higher time,
Yeah.
after after a certain subsystem size, the entanglement entropy will saturate, giving the
Correct.
area law kind of
Correct.
thing.
Correct.
So I was just wondering, is this the correct way of understanding it? That when the unitary dynamics begin
This
from a
plot,
ground
right?
state, which essentially has an area law of entanglement.
Sorry, talking about this plot, right?
Yeah, this plot exactly.
Okay, yeah, go on.
And then with time, so the correlations between the different spins, they start increasing. But since time
No,
is fine,
not the correlations is a slightly loose word. I should say entanglement. Okay.
okay, fine. The entanglement starts increasing,
Yeah.
but then since the time is bound, it's finite. So after that
Yeah.
time
Yeah. Yeah.
span,
Yeah.
the entanglement doesn't see the rest of the subsystem,
No,
and
so
hence it's
yeah, it's roughly correct. You're on the right track. So let me just sharpen your statement. So basically, suppose you start with a completely unentangled initial state.
hmm,
Okay. Then there is something called a light cone effect here
hmm,
on how the entanglement spreads.
hmm,
And typically, if you look at systems which are integrable or which are even more generic,
hmm,
so the only exceptions are many body integrable systems, which we'll touch upon during the last two lectures.
hmm,
Okay, there
hmm,
something else happens. Then typically for all the other systems where there is no localization mechanism, this
hmm,
entanglement entropy seems to propagate linearly in time. There is a sort of a quote unquote velocity, a well defined velocity. And this is
okay.
very interesting. So, for the integrable models,
Hmm,
even though integrable models are very simple, like this transversalizing model, where the entanglement is literally being carried by the quasi particles,
hmm,
for non integrable models, the situation is more subtle because there at high energies, this concept of quasi particles is gone, but nonetheless entanglement propagates linearly. Okay, but coming back to your question, so this is exactly what happens. So suppose you are at some fixed n, whatever
hmm,
n is here, then because there is a finite front of the entanglement which is going, then of
hmm,
course it can only spread so far,
hmm,
right? And
hmm.
after that, you will automatically see that the thing will cross over to an area law. So I hope that answers your question.
Okay, so for non-integrable system, will we see a similar behavior also?
Yes,
You're
yes,
saying?
you will see a similar behavior, but for entirely different reasons. Because, as I said, for this thing, you can understand it from a quasi-particle picture,
Yeah, yeah.
but there that description fails, and it's just that entanglement is much more peculiar than transport of local quantities. Okay, that's the short answer I can give you. Yeah.
All right. And one more naive question, maybe. Why do we expect an area law entanglement for the ground state? How can we argue about it?
The reason for that is in one dimension, if you look at gapped quantum systems, then there is a proof, and that's by Matt Hastings. That's called the Hastings Theorem. Okay.
Hmm?
And usually in 1D, okay, in higher dimensions, it's not strictly known. there's no theorem which tells you what happens in higher dimensions. But all the examples we know point to the fact that there should be an area law even in higher dimensions, right? Because ground states basically occupy sort of a tiny corner of your Hilbert space. They have some very specific properties. So of course, there's no proof in high dimensions, but all the known examples tell you that it should be area law. Yeah.
Okay. Okay. Thank you.
Okay. So any other questions from anybody? Okay, so if not, then let me continue with today's lecture. Let me cross this out, and yeah, this is today's lecture. Okay, so you see, yesterday we saw in reasonable detail that how to convert this problem of the 1D transverse field Ising model, which had interacting physical spins, into a problem of a bunch of pseudo spins, with each pseudo spin feeling its own magnetic field. Of course, yesterday we were studying the quenched problem, and in the quenched problem, I said that this G, this magnetic field, is independent of time. But if you just work out all the steps in my proof yesterday, you can easily convince yourself that this G can be an arbitrary function of time. Okay, and nothing of what I said yesterday would then fail. Okay, so this I encourage you to work out. The only thing that would replace everything that I was doing yesterday is you just put that function of time explicitly. That's it. So now, what I'm going to tell you very quickly, and hopefully it'll be clear to you, is that for these particular class of integrable models which map to free fermions, the Fluke problem, so the Fluke problem I can define as basically driving this magnetic field, this classical field, periodically in time. Okay, so basically now the system is a driven system. Now the energy is no longer conserved, right? Because I'm breaking time invariance in my problem. Okay, but nonetheless, I'm sticking with a driving which basically respects this property. Okay, it's some periodic function in time. Okay, so now the point is that essentially a very similar picture of what we talked about yesterday in terms of a generalized Gibbs ensemble would survive even here for the case of the transverse field Ising model, which goes to a problem of free fermions. Okay, so why is that so? So the reason for that is, if you remember yesterday, I said that there are all these conservation laws which define your generalized Gibbs ensemble, and there are basically an extensive number of conservation laws. And the way to geometrically understand those conservation laws is each pseudospin is moving under the influence of a magnetic field, right? A pseudo-magnetic field, if you wish. And this is basically the Z component of the magnetic field, and there's the X component of the magnetic field. Yesterday, there was no time dependence here. So, yeah. So then basically the motion of the point on the block sphere is on a great circle like this, right? Or like that, right? So each block sphere has its own conservation law. And in fact, this is intimately related to also the Bogoliubov transformation that we did. Okay, so there's basically a one-to-one relation. Okay, and those conservation laws, of course, helped us define the generalized Gibbs ensemble. Good. So now in this problem, there is a time dependence, right? So this axis, if you wish, keeps fluctuating in time, right? Why is that? That is simply because this G is a function of time. So of course, this guy is the same. The X component of the magnetic field is the same, but the Z component keeps fluctuating in time. So then you can very reasonably ask me, how can I then define a conservation law here? Because there is no unique direction to define the circle now, right? But the resolution to that in the Fluke problem is very simple. So here is the resolution. So as I said, when there's a periodic function in time, this magnetic field, then of course energy is no longer conserved. However, there is again an extensive number of new conserved quantities. So how do I know that? These extensive number of new conserved quantities emerge if I look at stroboscopic times. So for example, let's say I look at the system at time t equal to 0, capital T, T being the time period of your Fluke problem, capital 2T, 3T, and so on, right? Or if you want, you can put an arbitrary number epsilon here. Then you just go as epsilon plus capital T, epsilon plus capital 2T, and so on, right? So these are called stroboscopic times. They are separated by this time period of your drive. Okay. Then what you can show is for this particular integrable model is that if you look at the system at these intervals of time, okay, so now basically you can imagine that time is running as integers now, right? Then the basic object that you need to concentrate on is this u of t, okay? So what is this u of t? U of t is basically the unitary evolution for the system in the time interval capital T. Okay, so now because the Hamiltonian is time dependent, basically u of t is the time ordered exponential of minus I integral of ht dt, right? And you need time ordering because h at time t1 does not commute with h at time t2, right? But nonetheless, you can define this unitary time evolution for a unit of time which is equal to capital T, right? Then obviously the wave function at any other time n times capital T is just given by this formula, right? So what I'm claiming is, even though this system is now driven, this particular transverse field Ising model is now driven, but nonetheless it goes to a very well-defined steady state where again, of course, the entire wave function is a pure wave function, but again, I only concentrate on local operators, and these local operators go to well-defined values when n tends to infinity. Okay, so, but these are steady state values. Okay, so now, of course, as I said, the dynamics is given through a time-dependent magnetic field, right? So, but here comes the point. So for simplicity, of course, you can consider all kinds of periodic functions of time. There's an infinite class of them. But for simplicity, let me just consider a very simple class of periodic functions, where let's say the function is, the magnetic field is G1 for the first time interval capital T by 2, then it's G2 for the next time interval, and this keeps repeating in time. So this is, of course, a periodic function. Now, for this periodic function, it's very simple to write down the unitary matrix for each pseudospin. Remember, I can still write down the unitary matrix for each pseudospin separately, because you see, even if my problem is time dependent, of course, this pseudospin is seeing its own magnetic field, this pseudospin is seeing its own magnetic field, and so on. They are not being coupled to each other, right? Because of the integrability of the model, okay? Because of this equation, right? So, yeah. So, okay, right. So then, of course, you know from the study of spin half problems in quantum mechanics how to calculate this. You actually know how to combine these two unitary matrices, right? And you can then just write this unitary matrix. And then, of course, the resulting unitary matrix can always be expressed in this form, right? Where, again, you can define a new magnetic field. And this magnetic field is the effective magnetic field which each of the pseudospins sees if you're only concentrating on stroboscopic times, right? So this effective magnetic field, in particular its direction, because that's what I need to define the conserved quantity, right? This direction may be a complicated function of this G1 and G2, right? And if you choose some other periodic function, it will be a more complicated function. But nonetheless, it's some precise quantity which you can calculate, right? And so now this concept of a generalized Gibbs ensemble is simply replaced by a periodic generalized Gibbs ensemble when you are looking at the system stroboscopically in time, where these new conserved quantities are just dictated by these new directions, right? These directions are, of course, different from these directions, okay? Even though in my figure, I have sort of drawn them like that, maybe I should have drawn some new red arrows or something, just to show you that. Maybe I'll update that, okay? So these directions are now different from your old direction, right? But nonetheless, there are these precise directions again, right? And therefore, there are again an extensive number of conservation laws, again by the same principle that we talked about yesterday, right? And therefore, the concept of generalized Gibbs ensemble is straightforwardly replaced by the concept of a periodic generalized Gibbs ensemble for the case of transverse field Ising model or for other integrable problems where there is a free fermion structure. Okay, I should like to stress that this thing is not straightforward for other integrable models, which are, for example, Bethe integrable. There, probably there is no such generalization if you do the periodic in time problem, and it's still an open question. Also, in the latter half of the course, where we'll discuss interacting Fluke problems which are non-integrable, you would see that Fluke problems are completely different from quench problems. Okay, but for this particular example, because there is this very interesting mathematical structure, you see that immediately this generalized Gibbs ensemble is you basically replace it by this periodic generalized Gibbs ensemble, which again have a different set of extensive conserved quantities. Why different? Because these directions are now different. They depend on the specifications of your function g of p. Okay, but that's it. After that, everything else which I told you about goes through. Okay, so let me take a pause here and ask if there are any questions on this. So this is the Fluke generalization of the transfer-free Lysen model. Okay. Okay, so if there are no questions at this point, there's a question.
So in this time periodic case, is it possible to show that if you consider a sufficiently small subsystem, you actually end up with this GG state?
That's correct. That's correct. Anupam, so actually I showed that exactly in the lecture yesterday, right? So in the lecture yesterday, we exactly showed that you end up with the GGE for this particular case of the transfer-free Lysen model, right? So even in the periodically driven case, because all I'm saying is that your conserved quantities would change, okay? But nonetheless, the geometric picture is absolutely the same. So there is an equivalent thing there also. Yes. Yeah.
Okay. Thank you.
Yeah. But as I said, this is not true for, this is probably not true for other integrable models, which are maybe better integrable. There what happens for the Fluke problem is not so obvious. Yeah. But I just wanted to highlight this for the participants because here the generalization to the Fluke problem is completely straightforward in a interacting integrable spin problem. Yeah. So okay. So if there are no questions, then let me.
Hi, Arnab.
Yeah.
Yes. So I have a doubt that means why are you calling this GG as a periodic GG?
Oh yeah. So you see, I'm calling it as a periodic GG because you see, I needed to define this concept of a direction and these great circles. Okay. So now, if you don't look at times which are separated stroboscopically, then you cannot do that. Why? If you look at arbitrary time sequences, then this magnetic field is always changing as a function of time. The instantaneous magnetic field, it's always changing as a function of time. So there is no notion of a great circle, right? But if you look at it stroboscopically, then of course there are these new directions which again emerge, right? And then this concept reappears.
So here the Fluke unitary that we have. So the effective Hamiltonian of the Fluke unitary is actually is actually a GG.
Correct. It's actually a GG, right? So this you can think of as the Fluke Hamiltonian, this guy.
Okay.
And you can again write it in terms of the free fermions by doing Jordan-Wigner, and you will soon see if you do this exercise that Hamiltonian is very different from the static Hamiltonian.
Yes. It will be
because it's a Fluke problem, right? So,
yes.
But the nice thing about this geometric picture is you know that the same concepts go through. All you need to define is these new directions. That's it. So yeah. I mean, of course, the algebra may be a slightly harder thing, not very hard, but that's it. But everything else goes through.
Yeah. Thanks.
Okay.
One more small question.
Please.
Are there similar calculations for this periodic system? Similar calculations exist for classical systems?
So, Anupam, can you repeat your question? I didn't hear you properly.
No, I'm saying these periodic calculations. Does similar calculation exist for classical systems?
Okay, that's a good point. I'm not completely sure about this. So I'll say something and maybe people like Abhishek and if Manas is around, they can correct me, right? So you see, I'm looking at a problem with a large number of degrees of freedom. Okay, so So I mean, usually when we think of classical integrability, there are many things which we define for finite number of degrees of freedom. But I don't know. I mean, are there good examples where you can go to an infinite number of degrees of freedom? Okay, and if the answer to that is yes, then maybe something like this happens. But I haven't thought too carefully about that. Yeah.
No, maybe a harmonic chain is an integrable.
Okay. In that sense, yeah. So I think maybe something like this would happen. It should not heat up to infinite temperature. Yeah, probably. So yeah.
Yeah, I guess for harmonic chain or Toda maybe GG exists, but I don't know. Like with periodic driving, I haven't seen any.
Yeah. So maybe the thing to think about is again in a geometric sense. The real question is, so I think the bottom line is for a periodic drive, can you again define an extensive number of conserved quantities?
That is there, right? And that is of course there. Oh, for periodic driving, right? Okay, yeah.
No. So for periodic driving, if somehow you can extend this conservation laws to new conservation laws with an extensive number again, I think that's the real question to ask. Right, because you see, I exactly proceeded like that in this quantum mechanical problem, right? So yeah.
Right.
Okay. Good. Okay, so if there are no more questions on this point, then let me switch gears now, and then let me go to non-integrable systems from now on, from this point on. Okay, so as I already told you in my first lecture, most generic quantum systems, you would expect them to be non-integrable because integrable Hamiltonians are fine-tuned points. And more specifically, if you have these non-integrable quantum systems, then you would expect ETH to hold, eigenstate thermalization hypothesis to hold. At least most of the numerical and semi-analytical calculations and works suggest that. Okay, and in that case, the system should thermalize. Okay. And when I say thermalize only with respect to finite subsystems, because again, the system is in a pure state. Okay.
Arnab, sorry, just before you go to non-integrable system, maybe I can ask a question, but it's a bit naive, but even in your lecture yesterday, when you spoke about this power law decay of sigma x or something
of certain correlations,
correlations. So and also what you so the thing is, how much are these features related to the fact that it is free fermion type as opposed to Bethe integrable?
That's a good question. Of course, I frankly don't know the answer. Because as you know, for the Bethe integrable things, we cannot do so many calculations. But for the Heisenberg model, there have been some recent calculations. Maybe I'll check on that and come back to you on this point. For the free fermions, it's very straightforward to see that some quantities should decay as power law from a stationary point argument. But I'm not completely sure that whether there's such an argument for the Bethe integrable system, right? Because otherwise you expect exponential decays, okay?
Right.
So, because that's the generic thing. Power law decays happen because there is somehow this stationary sort of point picture, okay? So, so maybe I'll check that and get back to you on that question. Okay?
I mean, presumably, even if you have exponential decay in Bethe integrable, the decay is probably slower because of the underlying integrability.
That I would expect. Yes.
Right. Yeah. And just one more related question. I think yesterday also you showed some recurrence times, right? You were talking about some recurrence times, and it was rather fast, right? The recurrence was rather fast, right?
No, I mean, in my calculations yesterday, I was taking a very big system size and there was no recurrence, but there was a question from one of the participants, and there I said that if you take a finite system size, you would see weak recurrence, and the time scale would scale linearly with the system size.
Okay? Exactly. But if it is if it was Bethe integrable type, then
it might be different because they are not they are not like particles which are zooming past each other.
Right. Exactly. So
that's the intuition. Yeah.
Okay. Thanks. Sorry, I thought I'll ask you before you go to non-integrable systems. Okay. Thanks. Yeah.
Okay, good. So if there are no more questions, then let me switch gears and let me go to non-integrable systems. So first, I'll discuss a very particular kind of a non-integrable system, which has been the focus of a lot of research from sort of the past 4 years or so. Okay, because it was mainly because there was a remarkable experiment in the Lukin lab, and after that there was a flurry of theoretical works. Okay, and yeah, so yeah, so basically, so I'm going to talk about non-integrable systems, where there is a concept of a weak ergodicity breaking. So what do I mean by that? So what I mean by that is, so if you look at the left panel, so this is increasing energy. So while most of the high energy eigenstates satisfy the eigenstate thermalization hypothesis, there are some very peculiar states. Okay, and if you ask me what is the number of such states, now due to many theoretical works, I know specific examples where the number is order 1 in the thermodynamic limit. I know other examples where the number is order L in the thermodynamic limit. I also know other examples where the number is order alpha raised to the L in the thermodynamic limit. So there are various kinds of problems. But nonetheless, there are certain anomalous high energy eigenstates in your spectrum, in the high energy spectrum. Okay, and these are anomalous because even though they are in the high energy spectrum, they have a very low entanglement entropy. They don't satisfy the volume law. Okay, and if you look at local observables, they are the local observables. They are very anomalous. Okay, now you may ask, okay, they are scattered through your spectrum, but they still measure zero if you look at the entire sort of the entire available eigenstates here. So of course they won't show their signatures in thermodynamics. That is indeed right, but they can show their signatures in dynamics even if their number is order 1. Now why do I say that? So you remember I said that when you do an actual experiment or even these thought experiments to address questions like thermalization, your initial state is typically chosen to be a sort of a simple state which you can prepare in a lab easily, and that state has a low entanglement. It usually satisfies an area law entanglement. So imagine a situation in which the initial state that you have prepared, some simple initial state, has a large overlap with a bunch of these states. Then what you would see is, if you take arbitrary initial states, like in the example here, this is an actual calculation, by the way. Okay, this is an actual calculation, by the way. So, so if you take some initial states, I have just shown 3 initial states for simplicity. While most of the initial states, even though they start with very different values for their local observable, let's now ignore what this quantity is. It's some local observable. While they start with very different values, the unitary dynamics just locally equilibrates them and they reach the final value, same value, which is dictated by ETH. Okay. However, if you start with some simple initial states which have a large overlap with maybe some of these states, then even though their number is very small, in your actual calculation, you would see that this thing does not reach your ETH answer. Okay, so that is what I call as weak ergodicity breaking, because there's a class of simple initial states which show very anomalous dynamics. Okay, in these systems which are non-integrable. Okay, so I hope this motivation is clear to everyone. If not, then maybe if anyone has a question, I can answer. Otherwise, I'll go on. So this is the sort of thing that I would expect in systems which have these peculiar many-body stars. Okay, yeah. So there are dynamical signatures. Okay, when you look at quench experiments again, or yeah, or you do a thought experiment like the ones we were thinking about in lecture 1. Okay, so yeah. Okay, so was there a question? No.
So what is the origin?
Sorry, there was a question. Yeah. So can you just be a bit louder? I couldn't hear you properly.
Sir, can you hear me now?
Yeah, yeah.
So what is the origin of these anomalous states?
Yeah, so that is what we'll discuss in this lecture. Yeah, I mean, people are still not sure of, there seem to be multiple mechanisms for why such states emerge. Okay, and what I find really exciting is the following. Let me just share some of my excitement. There have been models which have been well known in condensed matter physics for the past 20, 30 years. Okay, they're like very standard models which people have studied for their ground state and low excitation properties. Now we are beginning to realize that some of those models actually have features like this. Okay, so the short answer to your question is that there are many open issues here of how such states can emerge. I'll give two possible mechanisms in this lecture if time permits. Okay, yeah. But yeah, the exciting thing is when we look at the spectrum of these very well-known models, then in some of these very well-known models, these things appear. Yeah. Okay.
So in the previous calculation, when you showed this mechanism for this ETH thermalization mechanism,
yeah,
where you showed that there is a first term and then the second term, that second term was oscillating, that you neglected in the first term, where you had a very narrow this thing, and so you took out the what breaks?
Oh yeah, correct. So Anupam, as I said, what breaks is those two things don't break. So still the energy distribution is narrow. So remember I was talking of mod of Ci whole square and all those things, right? So those distributions are still narrow. Nothing breaks there. The thing that breaks is, you see, I needed to pull that mod Ci square outside my sum, and I demanded that ETH is true for all high energy states. That assumption breaks down here, because I'm saying that some of the high energy states don't satisfy ETH square. So that is the thing that is breaking down.
I see.
Okay. Yeah. But for most initial conditions, of course, the overlap Ci square would be very small to these states. So you would not notice their effect. But for some initial conditions, if the overlap is very big to these states, then you would notice their effect. That's the answer to your question.
Yes. Okay.
Okay. Yeah. Okay. So what is this experiment that I was talking about, which sort of was a driving force for many of these new things? So there was a experiment which was done around 2017, which basically took a chain of one-dimensional Rydberg atoms, and essentially they could take a reasonably big quantum simulator with 51 qubits. So that is already quite impressive. Okay, so after that, other groups have sort of increased this number. Okay, and it was sort of an interacting model. Okay, so basically it was a Rydberg atom problem, and without going into too much detail, essentially one can still think of it as a spin half problem, because this Rydberg atom could either be in its ground state or in a highly excited Rydberg state. Okay, so basically it's like a two-state problem. And the quantum dynamics is that the ground state can go to a ground state at a particular site of the Rydberg atom can go to its excited state and vice versa. Okay, but it's some interacting problem of Rydberg atoms, and with 51 qubits, your Hilbert space is rather large, right? Because it's roughly like 2 raised to the power 51. So that's a huge number. Okay, so you would expect thermalization there, because you have a very large Hilbert space, and so your density of states is very high, and so you should expect ETH, right? Because you should see all kinds of things related to random matrix theory and so on. Yeah. So okay, but what they saw was the following. They took many initial conditions and quenched them in their experiment. But in particular, let us focus on two initial conditions. Both those initial conditions have the same energy density. In fact, both those initial conditions lie in the middle of the spectrum for them. So they are like infinite temperature initial conditions, if you wish, because they are sort of at the middle of your energy spectrum. Okay. So one initial condition was your Rydberg vacuum initial condition. So all the atoms, all the 51 atoms were in their Rydberg ground state. Okay. While the other initial condition was that it is like a nail state. So what do I mean by that? So it's a 1D chain. So let's say the first Rydberg atom is in its excited state, then the second is in its ground state, the third is in its excited state, the fourth is in its ground state, and so on. Okay. So That is another initial condition. Okay, so this initial condition and this initial condition both have the same energy density, both are high energy initial conditions. Okay, now let's quench them. You expect that both of them would thermalize to the same thing. Okay, now this is a theoretical calculation based on a minimal model, and this basically reproduces what they also saw in their experiment. Okay, so I'll come to this theoretical model for the rest of my talk. And sorry, I forgot to make an announcement. Of course, there are some details which I'll skip for this theoretical model, certain technical things. But in tonight's tutorial session from 6 p.m. onwards, Bhaskar Mukherjee will talk about some features of these exact diagonalization in non-integrable systems and level statistics, and also some other features of these this interesting minimal model, which I'll soon introduce. It's called the PXP model. Okay, so Bhaskar will sort of discuss some numerical details about that, and so interested participants can, of course, interact during that session tonight, and yeah, so there'll be more details. Okay, yeah. So what happens is rather interesting, and this is also what they saw in their experiment. So while this state, which I denote in red, while this state quickly thermalizes to the ETH answer, I'm looking at some local quantity, local correlation function again. So let's not go into the detail now. So while this thing quickly thermalizes to its ETH predicted answer, this blue line indicates that. If you look at this other state, this null state, or the state with an alternating array of Rydberg ground state and excited state, or in the spin language, it's just up, down, up, down, up, down, up, down, right? If you look at that state, then you see something remarkable. You see that even though, you know, you're looking at the middle of the spectrum with a large density of states, this thing just keeps coherently oscillating to its sort of translated partner, which is 0, 1, 0, 1, 0, 1, back and forth, right? Like this. So of course there is a sort of a slight decay in this, what should I say, in this oscillation strength, but you see there are these anomalous oscillations, right? This is more reminiscent of like a free spin problem or something like that that we were seeing in our integrable model yesterday, right? But this is a highly non-integrable model, and it's completely non-obvious what's happening here. So the bottom line is, even though most initial states quickly thermalize in their experiment, few initial states like this one actually show very peculiar coherent oscillations. And there is a frequency scale to that oscillation, right? There's a frequency scale here. You can ask how that frequency scale emerges here, right? Because here in the high energy spectrum here, the level spacing between different energy eigenstates is exponentially small in system size. So you can also ask, how on earth does that energy scale emerge here? So I hope this mystery is clear to you, right? Because I mean, even if we don't know anything about non-integrable models and quantum stars, I mean, even this slide should tell you that there's something very peculiar happening here. Okay, so we'll now understand why this is happening through a particular minimal model to mimic this experiment. Okay, so this is what we are going to do. Yeah.
No, but what was this observable O22? Or
sorry, so I didn't explain it here. So this observable is Abhishek, just a two-spin correlation.
Okay.
Yeah, it's just a two-side correlation like this, right? So you see, the two-side correlation of this guy is 1, basically, right? But the two-side correlation of this guy is 0, right? So this graph tells you that the system is going from here to here to here, back and forth. You see? Okay.
Okay.
Yeah, yeah.
And there were, I think, a couple of chat questions related to the previous slide, probably.
Oh. Is it possible that you can read them to me? Sorry about this.
Yeah.
Sorry.
So the first one is, if you go to, so what exactly is I and J in the quantity plotting on the y-axis here?
So as I said, please forget about that now. If I have time, I'll introduce it later. It's in some particular problem in a non-integrable model. I haven't defined that problem. Because it's a non-integrable model, most initial states thermalize, and this is some local correlation function. But there are some initial states which do not thermalize. That is all I wanted to say here. If I have time, I'll go to the details. Yeah.
Okay, but this is I and J are energy levels, right?
No. Sorry, maybe that was the confusion. I'm sorry.
Yeah.
yeah, so this is bad notation. This I and J are some electric flux correlation in that other problem.
Okay.
They are some local quantities. Okay. And the expectation value is taken with respect to the many body wave function. Okay, sorry about that. So maybe that caused the confusion. Yeah.
Okay. And the next question is, how does one check analytically or numerically for the existence of such anomalous states in a given model, given that the measure of such states is zero?
Yeah. So we'll come to that. We'll come to that during the course of this lecture. And also this will be discussed more by Bhaskar in his tutorial tonight. Yeah. But we'll touch upon this in the course of this lecture itself. Yeah. Okay. So I think I can go on.
Yeah.
Yeah. Okay, good. So now, what is this relation to quantum scars? So this thing about quantum scars was sort of well known in a few body quantum mechanics for quite a while now, based on pioneering works from Heller. Basically, this problem has a classical origin. This particular thing, this one body thing. So suppose you take this billiard problem, which is well known. So there is a particle which is sort of scattering elastically through the boundaries. Now, if you take a circular billiard thing, and here I've shown multiple paths here. Now, even if you take several paths here, there's nothing chaotic in the sense that the path don't cover the internal region here of the circular billiard. And the answer to why this happens is straightforward. Not only is energy conserved here, but because there's a circular symmetry, there's something like a conservation of an angular momentum here as well. So your phase space, which is two-dimensional, is sort of integrable here because there are two conservation laws, right? But now, suppose you don't take a circle, now you take a more complicated shape like the stadium problem. Then, of course, if you start with multiple initial conditions, I have taken all the colors to be the same here. But anyway, if you take multiple initial conditions, then if you just propagate them, then very quickly you will see that you will sort of densely populate the interior of this thing. And that's simply because this problem is chaotic, right? In a classical mechanics sense, because there's only one conservation law here, which is energy. The other conservation law is not there anymore because of the shape of this boundary. Okay. Now, suppose you ask what happens to the corresponding quantum mechanical problem. So, what is the corresponding quantum mechanical problem? All you're doing is you're taking a free particle again, and the particle has these hard constraints at the boundary, right? The wave function sort of has to vanish at the boundary. Of course, we can easily solve such problems for simple boundary conditions, but this is a more complicated boundary condition. So you cannot solve it analytically, and you have to do it on a computer. Okay. Now, suppose you do it on a computer, and you get these wave functions as a function of space x, let's say. So you call a wave function psi of x. So let me say psi subscript I of x, where I runs from whatever 1 till whatever, however many wave functions you can accommodate here. Okay. Now, if you look at any I which is reasonably high, because you want to be in the middle of the spectrum for your quantum problem, and you plot mod of psi square as a function of space, then typically you would see that that function would be reasonably delocalized inside the stadium. But you would see that once in a while, there will be some very particular values of I where this probability function, the square of the wave function in space, if you plot that, that will be very anomalous. So I have shown one numerical example here. So it will be very anomalous. This is clearly not sort of delocalized inside this thing. Okay. Now, this is like a quantum scar because its wave function is very, very different from the neighboring wave functions. Okay. Right. So, of course, there's a one body problem. Okay. And of course, this has a classical origin here in this simple thing, in the sense that there are these classical paths which you can almost see here. Right. So even in this problem, there are special classical paths, which if you start the problem precisely at those paths, the problem would stay here. The problem would stay here, and it would not become chaotic. But of course, if you perturb that path slightly, then it will become chaotic. Okay. So basically, it's the remnant of those paths here in this problem. Okay. So this is rather well explored in quantum mechanics as well since the time of Heller. And this has these kinds of things have also been observed beautifully in experiments. People do some very clever experiments using, I think, cavity and radiation, where they can mimic such a quantum process, and then they see these anomalous things, and they also see non-anomalous things and all that, right? Now the question is there a many-body version of this? Okay, so indeed there is. So now I'll go back to trying to mimic this experiment. Okay, so now I'll model this experiment by a effective spin half Hamiltonian. Okay, so as I said, the Rydberg atom can be thought of as a spin half problem, because basically there are only two important states. One is the Rydberg ground state and one is the Rydberg excitation, right? So I call the Rydberg ground state as being sigma I z being -1, and the other guy is +1. And of course, there's again a 1D lattice because their experiment was in 1D. Now, what is the minimal quantum dynamics you can have here? The minimal quantum dynamics is that you try to flip a excitation to its ground state and vice versa. So that operator is sigma x. Okay. Now there is a very crucial bit here. So typically in Rydberg atoms, there is some phenomenon called Rydberg blocking, which basically tells you that there is a huge energy cost in putting neighboring Rydberg atoms together in their Rydberg high energy excitation state. Okay, so yeah, so this phenomenon is called Rydberg blocking. Okay, and so basically, what does that phenomenon do to a spin problem? So basically, if I just say that my Rydberg blockade energy scale is just infinity, okay, it's some huge energy scale because I want a simple theoretical model, then what it's telling me is that in my spin half lattice problem, I cannot have two simultaneous upspins. That's what it's telling me. Because if I have two simultaneous upspins, then it basically means that I'm paying this Rydberg energy blockade cost. And I don't want to do that. Okay. But of course, I can have one spin being down and the other spin being up. Okay. One spin being up here and the other being down and so on. Right. So these other configurations are allowed, but this configuration is not allowed. Okay. Yeah. I hope this is clear. Right. This I just demand from the experimental constraint that there is a strong Rydberg block. That's it. Okay, so I'm trying to mimic the experiment in the most simple bare bone manner. Okay, good. So with this constraint, let us again consider the SZ basis with periodic boundary conditions with capital L states. Now it should be completely obvious to you that the number of allowed states is no longer 2 raised to the power L, where L is the number of sites. It's something smaller, much smaller. Okay, why? Because I mean, suppose I arbitrarily draw spin configuration here. Any spin configuration in which any two neighbors, including the periodic boundary ones, in which any two neighbors are simultaneously up, I just throw it out of my Hilbert space. Okay, so of course this number would be significantly different from 2 raised to the power L. So actually, this is a nice statmic problem. Suppose I ask you how many states are there? It's not 2 raised to the power L, it's alpha raised to the power L. So I ask you, what is that number alpha? It's not 2, it's something less than 2. Now, there is a nice way of just calculating that using transfer matrices. So I'm sort of running out of time, so I won't go through that detail. But basically, what you can just show is the answer is that if you are at a system size L with periodic boundary conditions, the number of allowed states that you have, is basically f of L minus 1 plus f of L plus 1, where these f's are Fibonacci numbers. Okay, so the definition of Fibonacci numbers is given here. There's the standard definition. F1 is equal to F2 is equal to 1. Okay, and Fn plus 1 is the next Fibonacci number, Fn plus 2. And now if you take L being a large number, from the way Fibonacci numbers behave, you can easily show that this 2 raised to the power L is replaced by phi raised to the power L, where phi is nothing but the golden mean. And the golden mean is a well-known irrational number. It's something like 1.61 something. And that's it. That's the number of states that you're allowed in your Hilbert space. So that's the first important ingredient. So the first important ingredient is that I have a constrained Hilbert space. Okay, so a constrained Hilbert space means that I cannot flip a spin arbitrarily. If I flip, let's say this spin, then, and if that spin goes up, then this flip is not allowed because I have a constraint in my Hilbert space. That's a hard constraint. Okay, so this is a constrained Hilbert space. And that's why the dimension of this Hilbert space is not 2 to the L for spin half. It's something smaller. Okay. Yeah, I mean, are there any questions till this point? If not, then okay. So now let me try to introduce quantum dynamics in this constrained Hilbert space. So what is the simplest quantum dynamics you can think of? The simplest quantum dynamics you can think of is this. Okay, so when I say simplest, I mean most local. Okay, so the most local quantum dynamics you can think of is this, right? So yeah, but see, this quantum dynamics cannot work because this does not satisfy my hard constraint. Now this is very easy to see. Now let me start with a particular SZ state. I don't care about the rest of the spins. So 0 means -1 in my notation and 1 means +1. Sorry, sometimes there's an abuse of notation, right? So yeah. So suppose I try to flip this spin, okay, because that is what this Hamiltonian would try to do. But then that's not possible, right? Because if I make this guy up here, then this guy is up and this guy is up, and this violates my constraint. So this thing is not a legitimate Hamiltonian in my constrained Hilbert space. Now the question is, what is the most local legitimate Hamiltonian? The answer is very simple. I want to flip a spin locally, okay? And I want to always satisfy the constraint no matter whether it's down or up. Then you can easily convince yourself that the only way I can do that is if both of its neighbors are down. Okay, if both of its neighbors are down, I can freely make this spin to be down or up. Okay, I can freely do that. Okay, so therefore, the minimal quantum Hamiltonian or the minimal quantum dynamics I can write here is this so-called PXP Hamiltonian. Okay, this is this PXP Hamiltonian. So what is this PXP Hamiltonian? I want to ensure this condition when this operator acts, right? Therefore, I have these projectors. So all that these projectors are doing is, so this projectors, if this projector acts on a downspin, it gives you the downspin. If it acts on an upspin, it gives you an upspin. And this guy is 1 minus sigma z j by 2. So this is the full Hamiltonian, okay? And of course, if you multiply all of these terms, you will see it's an interacting Hamiltonian because there are higher spin terms here, right? But this Hamiltonian is a legitimate Hamiltonian in my constrained Hilbert space, and it's the most local Hamiltonian in my constrained Hilbert space. It's the minimal Hamiltonian that I can write. And in literature, this is called the PXP Hamiltonian because this is a projector, this is like an X, and this is like a projector again. So that's why it's called the PXP Hamiltonian. So was there any question? Maybe I heard some question or a comment.
Status क्या है? MSP क्या है?
Hello.
MSD
Sorry, is there any question from Rupak? Sorry, Abhishek, is it just me or can you also hear something?
Yeah, Rupak, I mean, do you have a question? Rupak? Okay, maybe it's just a mistake.
Yeah. Okay, yeah. So now you see, so this PXP model has been a focus of a lot of works after that 2017 experiment. Okay, but this PXP model was actually, in fact, a generalized version of this exact model was actually written by Subir Sachdev, Krishnendu Sengupta, and Steve Gurman in a paper much earlier than 2017 or 18. Okay, so in fact, these guys were trying to look at the problem of a Mott insulator in a strong electric field in one dimension. Okay, and they just wrote an effective low energy Hamiltonian, and that effective low energy Hamiltonian lived in a constrained Hilbert space, and it had exactly this form. Okay, and this is usually how constrained Hilbert spaces also arise in condensed matter. This is something well known. Okay, so you see, here is an example of a model which was actually well known. from a long time, but these guys were, of course, just interested in sort of the ground state and the low energy properties of this model. Therefore, they could not figure out the scars in the spectrum of this model. But after that, people realized that there are scars. Okay, so somebody might object and say, why am I saying that this model is non-integrable? Maybe this model is not non-integrable. Okay, so now, how do I know that this model is non-integrable? This would be covered in more detail by Bhaskar during the tutorial tonight. So suppose I do exact diagonalization on this model. So one thing which I forgot to mention, which is very important, is, of course, anybody who has done exact diagonalization knows that you cannot do very big systems. And if you want to do bigger systems, you need to implement the symmetries of the problem. Okay, so now there is a very important point here. If you want to test whether eigenstate hypothesis is true by looking at something called level spacing of your energy spectrum in the eigenvalues, then it's actually extremely important to implement all the global symmetries of your Hamiltonian and look at the symmetry resolved sector only. Okay, that's a very important comment. So this model has two global symmetries. One is the translation invariance. Okay, one is translation invariance because I'm defining it on a ring, and the other symmetry is a discrete spatial inversion symmetry. So basically, you take the ring, okay, you cut the ring along the line which passes through any of the bond of the ring, okay, and you just reflect your system about that bond. Okay, that's a discrete symmetry, and that's like an inversion symmetry. That's also a symmetry of this model. So if you resolve both these symmetries while doing your ED, and you go to a particular symmetry sector, for example, we go to k equal to 0 with this other quantum number, this discrete inversion symmetry quantum number being +1, that can only be +1 or -1 because it's like a discrete Z2 symmetry. So suppose I go to this guy, and then if you look at the level spacing statistics from your computer by doing a reasonable system, maybe the system size that you take is something like 24 or 26. Okay. Okay, now there's another point here, which is important. The reason you can take a size of 24 or 26 here is because unlike spin half systems, where the Hilbert space goes as 2 raised to the power L, here the Hilbert space goes as the golden mean raised to the power L. So you can go slightly bigger in system size. Okay. So if you do that, and then if you look at your level statistics, I won't have the time to explain that, but I think probably you may have encountered this already a bit in Gregoire's lecture. Okay. So then for non-integrable models, because there's something called a level repulsion, then basically you see a level statistics which is like this, which goes to 0 near 0. Okay, and this is called Wigner-Dyson. Whereas if you had an integrable model, even if you resolve the obvious global symmetries, because there are other hidden symmetries, you don't see level repulsion. So you see something called a Poisson statistics. Okay, so for this PXP model, you beautifully see, at least for the system sizes that one can access numerically, that there is Wigner-Dyson statistics. Okay. So this proves that this model is non-integrable, at least for the system sizes you can access, and it's highly unlikely that it will suddenly become integrable. Okay, good. However, in your analytic calculation, if you start with a state Z2, so what was my Z2 state? It's this up, down, up, down, up, down state. If you start with the Z2 state, and if you actually calculate the return probability in the many body dynamics. Note, I'm not even calculating a local correlation function. I'm literally calculating the return probability. Okay. So you start with Z2, you do a time evolution, then you overlap with Z2 again, and you take a mod square. That's the return probability of the full many body wave function. Then please look at the blue line. I'll explain later in one slide what the green line is. Please look at the blue line. The blue line is the answer for the PXP model. You see, of course, this quantity starts from 1 at time t equal to 0. But the expectation is that for a many body interacting system, it just quickly decays to 0, exponentially fast. So initially you see that, but then something remarkable happens. Then it revives. then again, so sorry, please follow the blue line. Of course, it doesn't define perfectly to 1. I'll explain the reason for that. But then it again decays, then it again revives, then it again decays. And there's a frequency scale here, which is some omega. And this omega is precisely equal to this frequency scale here. Okay, so basically it's related to this frequency scale. Okay, so yeah, so basically you see even the many body wave function is doing something very strange, even though it's a high energy wave function. So maybe I'll take a pause here and ask if there are any questions up to this point.
Arnab,
yeah,
this beyond this level repulsion, this plot.
Yeah.
So like this quantity Gregory was mentioning yesterday, like number within a given region, for example, the fluctuation.
Yeah. So I'll show you some other quantities, Sanjib. Yeah. Yeah.
Okay. So do you see like this RMT kind of thing?
We see signatures of ETH. That's absolutely correct. Yeah. So I'll show you in the next slide. Yeah. So here is the answer to Sanjib's question. So remember I said that if ETH is true, then you know the answer should mimic thermal answers, right? If you look at local correlation functions. So Z1 is basically sigma 1 expectation at some particular site. Okay. So that's Z1. Okay. So this figure is taken from this particular paper. Okay. So by the way, these two papers are the theoretical papers which introduced this PXP model after that experiment was done and showed why that experiment had these anomalous oscillations. Okay. So these are the two papers. Okay. So yeah. So there, hello, is there a question?
Yes or no? So the characteristic frequency that we are seeing in the revival, so it depends on what feature of the Hamiltonian?
No. So that's very subtle. I'll come to that. So you cannot stare at the Hamiltonian and guess that. So of course that depends on this number W. But that's a trivial statement. That's a trivial statement. This frequency is some alpha times this number, right? That alpha is a very non-trivial number. I cannot guess that just by staring at this Hamiltonian.
Okay. So I'm asking that because let's say if I'm expanding my initial state in the eigenbasis of PXP Hamiltonian, so in that case, right.
But Naveen, you're asking a very difficult question, right?
Sorry.
No. I'll explain to you. See, these expansions and things like that, these are all perturbative pictures, right? What you're saying, right? These only hold true near the ground state, right? That's what we learn in statistical mechanics courses. We are talking of high energy. Okay. I'll show you whatever time will permit, but I think my lecture will spill over even in lecture 4. That's okay. I mean, I'm always happy to address questions. What I'll show you is due to some very subtle reasons, okay, somehow some of the high energy states behave in a very peculiar fashion. And they behave in a very different fashion to the other high energy states. Okay, but you cannot do naive perturbation theory here. That's impossible. Okay. So, yeah. And of course, if you knew the eigenstates, of course you can calculate everything. But you see, knowing the eigenstate of an interacting spin problem is an exponentially hard problem. That's why we are doing exact diagonalization here. I mean, I don't know them analytically, right? So
yes.
Yeah. I hope that addresses your question.
Yes or no? Thanks.
Okay. Yeah.
No, I had a couple of questions.
Yes.
So one is this oscillations that you see in the Z2 state. These were already seen in this 2002 paper or no?
No.
This is new.
Abhishek, no, absolutely not. Because see, that is what I'm saying. See, remember in my introduction, I said that these quantum scars, one of the very exciting thing about them is that there are some very well-known condensed matter models where people are now looking at the entire spectrum and they are realizing that they have quantum scars. Okay.
Right. Yeah.
In fact, towards the latter half of my talk, and maybe that will go to the first half tomorrow because of the time. Okay. I'll in fact show that even well-known models like quantum link models or quantum dimer models, right? These models have a huge history in condensed matter, right? Even they have quantum scars.
Okay. So these oscillations were seen more recently.
Exactly. So what Krishnendu and Subir and Gerwin, what they were looking at was the low energy part of this effective model, right? because they were concentrated with the phase diagram and quantum phase transitions and things like that. Okay. So,
but even the the level statistics, it's not from their paper, is it?
No. The level statistics is not from their paper. Sorry, I did not mention that maybe. So the level statistics I have taken from this paper. This nature paper, this one.
Right. Okay. And the other question is, I guess maybe you'll explain this. So these oscillations, they are not from the exact solution, but from some perturbation theory, is it? Not from the numerical diagonalization.
No. This plot is a numerical plot. As I answered Naveen right now, because I'm looking at high energy states, it's incredibly complicated. It's incredibly complicated to actually do this analytically. However, in today's talk, I'll give you a physical picture and a toy model where this can be exactly done. The PSP model is probably sort of encapsulating that physical picture, but several details need to be filled. Okay, that's the answer to your question.
Okay, no, but in this plot, what are the zeroth order, first order?
So as I said, I'll explain these things later. Sorry, these are some, maybe Bhaskar will also explain that in his tutorial.
Okay.
So, sorry, this perturbation is some different perturbation. This is not the standard perturbation. Yeah.
Okay.
Sorry. but this blue line is, for example, a numerical plot.
Okay.
Yeah. So you just literally take your state and you just do ED. Okay. On a system with maybe, I think, 24 or 26 pins for this plot.
Right.
Okay. Yeah. Any further questions?
Arnab, just one quick question. So how important was it that phi turns out to become irrational number here?
No, that's not terribly important, Manas. But phi, yeah, that's not terribly important. But phi has to be a non-trivial model because it's a constraint model.
Right.
But I can pose your question differently. You can ask, are there quantum scars seen in other interacting theories which don't have a constraint Hilbert space, right? That's one way of posing your question. Okay.
Or which have a constraint Hilbert space of the form some rational number power n.
No, but I can even give you a simpler answer, right? Suppose they have an unconstrained Hilbert space, then this thing is 2 raised to the power L or 3 raised to the power L or something like that.
Right.
Then the answer to that is one can construct models like that. Again, it's very, very interesting. That's why I'm excited about this. So in one of the works which I was also involved in, there are some frustrated spin models which have been again known for 20 years or so. Okay. And yeah, in fact, I'll present another model which is also very well-known frustrated model maybe tomorrow. And again, that's known for 20 to 30 years and they have scars. The model which I'll present has a constrained Hilbert space, but the model which I'll not present does not have a constrained Hilbert space. It's I mean, it's similar to the Shastri-Sutherland model. There are models like that. Yeah. So.
Okay. Thanks.
So, I mean, I think in response to also Abhishek's question. So see, if there are perfect revivals, I would call them exact scars. Okay. In my language. But if there are these revivals like this, like in the PSP model, I would call them approximate scars. Okay. And I think it's obvious why I'm calling them approximate scars. I'll say a bit more about that, right? I think these approximate scars are much more abundant in interacting theories. That's my statement. I don't have any proof for that. That's just a hunch. But I think the recent developments may suggest that these approximate scars are more commonplace than we might have thought in interacting theories. Perfect scars are again fine-tuned, just like integrable points. But you see, Manas, what I'm trying to say. These approximate scars may not be so fine-tuned. Yeah?
Right. Yeah. Right. Thanks.
Okay, so sorry, I think I did not complete the answer to Sanjib's question. So there is this color gradient here, right? And I have been told by Bhaskar that this is the standard gradient used in Python. Okay, and warm colors indicate high density of states. So I'll go with that. So you see, wherever the density of states is very high, so Sanjib, you see that the answer is going to the canonical answer, right? These black guys and the other guys don't have such a big density of states. I mean, they are some, But the things with a high energy, with a high density of states, they are going to your canonical answer, and that's basically consistent with the eigenstate thermalization hypothesis. Okay, and you can look at other quantities as well. Okay, so yeah. However, here is the important point. I have marked some states with crosses here, as you can see. Okay, see, these states are high energy states. Why are they high energy states? Because you see, I told you, okay, I did not tell you this, maybe I'll tell you this later. The spectrum of the PXP model has an E2 minus E symmetry. I'll tell you the reason later, but you can see it from the data itself. There's an E2 minus E symmetry in the eigenvalues. Okay, and basically this number E, which is basically the range of this x-axis, this increases extensively with your system size, right? Because it's an interacting theory. Okay, so it increases extensively with your system size, the range in your x-axis. But let's say you look close to equal to 0. So that's like infinite temperature. You see all these anomalous states here. These are your quantum stars. These are your quantum stars. The things which I've crossed out. Okay, these are your quantum stars. These are very different from your canonical answers, even though their energies are basically the same as the energy here. So they violate ETH. Clearly, they violate ETH. Okay. In fact, this graph has much more structure. I don't think the time will permit to discuss all that, but later sometime, or if somebody has questions, we can correspond on that. But okay, yeah. So now, why do we see these scars importantly in the dynamics when we look at the Z2 state? Because if I look at the overlap of the Z2 state with all the energy eigenstates here, the Z2 state has a rather high overlap with the scar states. Exactly like I said in my introductory slide in today's lecture. That's why the Z2 state, which is a simple initial state, shows these revivals, right? If you took a 0 state here, which is the Rydberg vacuum, then you would just see this thing crash to 0 and stay to 0, okay? Modulo recurrence effects, that's it, okay? It would not show any revivals, okay? Because the 0 state, which is again at the same energy density as the Z2 state, the 0 state does not have significant overlap with the scar states. It's just the Z2 states which has a significant overlap, okay? And these scar states, I have not shown the plot here. Maybe I'll insert that later. These scar states have a much smaller entanglement than these typical states which satisfy ETH. These scar states seem to have a logarithmic scaling of entanglement, okay? They don't seem to have a volume law scaling. These other states seem to have a volume law scaling numerically, but these scar states seem to have a logarithmic scaling with entanglement. Now let us ask ourselves some simple-minded question. Here I seem to see a problem with weird anomalous states which are equally spaced in energy, and this is another numerical observation. If I increase my system size, I see that the number of these anomalous states increases extensively. Okay, so these crosses, these absolute outliers. By the way, some of these states are also close to the ground state, but you can see when you do your ED that there's a rainbow of these outliers. I've marked all of them. All of them have the same origin, okay, similar origin. It's just that some of them are low energy and others are high energy, okay. So actually, it's a very beautiful thing. I won't be able to expand on that during this lecture. So some properties of the low energy phase diagram, in fact, get reflected in the high energy phase diagram. But I won't have opportunity to discuss that in this lecture because it's beyond the scope of that. Okay. Okay. Yeah.
So in the first plot, what is plotted in the y-axis? The Z1 quantity?
Energy. Sorry. In the y-axis, this Z1 is basically sigma 1z on some particular side. Okay.
Okay.
Sigma 1z, some local operator. Sigma 1z. Okay. Yeah. So okay. So you see, all this would remind us of a giant SU2 spin where the length of the spin is order L, somehow protected in my Hilbert space. Okay, because a giant spin L has L+1 states, right? Let's say there's a spin L by 2. Okay, spin L by 2. That spin L by 2 has 2 times L by 2 plus 1, which equals L plus 1, that many number of states, right? So somehow all this thing is reminding us of a giant SU2 spin in my high energy subspace, somehow being protected by the rest of the Hilbert space. Okay. So now why does this happen? Because as I think many of you asked, in high energy subspace, there's no obvious way to do perturbation theory, right? So how on earth is this SU2 spin, giant SU2 spin being protected, even though there are so many states which are exponentially close in energy, right, to these particular states? I mean, why can't we do perturbation at high energy typically? Because no matter how small your perturbation is, you can always find neighboring energy states which have a finite matrix element with respect to your perturbation, but the energy denominator is very, very small, right? That's why your perturbation blows up, right? That's the usual argument, okay? So what protects us here, okay? So let's see. So here is my theoretical slide. So this is a picture. Most likely some variant of this picture is true. Most likely some variant of this picture is true in the PSP model. We do not know yet how it's true. Okay, but let me present the picture. So this picture is that there is probably a non-generic breaking of a symmetry. What do I mean by that? Usually in quantum mechanics, all interesting things happen when you take a problem which has a particular symmetry and you introduce a term which breaks that symmetry, and then you see that consequences of breaking of that symmetry, right? And of course, as we know from our studies of condensed matter, group theory, everything, the consequences of breaking of symmetry are actually very, very interesting, right? And in fact, most of condensed matter deals with questions like that, right? Many things in condensed matter, right? And in statistical mechanics as well. Now, what do I mean by non-generic breaking of a symmetry? And again, the term that I would add in my Hamiltonian is a non-generic local perturbation. So what do I mean by that? So let me start with the original problem, which is, let's say, very simple. And let's say it has some obvious symmetry. So on my computer, when I do exact diagonalization, I can block diagonalize with respect to that symmetry. So of course, there are some blocks which are very large. There are other blocks which are small and so on. Let me give you a very trivial example. Suppose there is a spin problem that you take where total Sz is conserved. Then of course, the largest block is typically when Sz is 0. And the smaller blocks are when Sz is some large number. Okay. So there's a hierarchy of these sizes when you do ET. Okay. But one block is disconnected to the other because they are symmetry decoupled. Okay. Because your Hamiltonian has that symmetry. So let me just start with a toy problem, which is some simple problem, and I can obviously write that. It may not even be a simple problem, but let's say I just even know that there is some symmetry like that. Okay. Now I do something which is rather peculiar, and it's not always obvious that you can do it. Okay. So let's say there is some corner in my Hilbert space. Okay, there is some reason why this corner cannot be very big in your Hilbert space, why it can be typically order L cross L. See, your Hilbert space is exponential L cross exponential L. But basically, what I'm going to say can only work if this corner is typically order L or smaller, because otherwise this perturbation cannot be local. Okay, but I won't have time to explain that. Okay, I mean, yeah, sorry. So let's say there is some corner, typically let's say the smallest corner, okay, in your Hilbert space, where let's say I introduce a perturbation which violates the symmetry. So if I introduce a perturbation which violates the symmetry, but it's a local in space perturbation again, if it violates the symmetry, then all these sectors are mixed, obviously, right? All these sectors are mixed. And let's say it's some generic interacting perturbation. But somehow this local perturbation, when it acts on this corner, it exactly annihilates the states in this corner. So let's say this is some perturbation, let's say some term V acting on any state here. So V acting on any state here gives you 0 times that state. Now this is highly non-generic. I mean, a typical thing would also mix this guy with this guy with this guy, everything, right? But suppose I could construct a perturbation like that. suppose. Then what you would immediately see is that all these other sectors mix and ETH is restored, whereas this corner in Hilbert space survives on its own. And it survives because this non-generic local perturbation, even though it's an interacting perturbation, it does not touch this corner. It annihilates this corner. That's an exact statement. Okay. So now this might sound very weird to you. You might ask me, can I ever do that? Now let me show you a model where I can do that. Okay, and that should lay your fears to rest. But of course, this is a non-generic breaking of a perturbation. Okay, so let's see. Let's actually look at a toy problem. So this is a toy problem. This is much simpler than the PXP model. So again, let me consider capital L number of spin halves on a ring. Okay, and now this is related to Manas's question. Manas, there is no constrained Hilbert space here. So this toy model would have exact scars without any constrained Hilbert space. So so then the Hilbert space is obviously 2 raised to the power L. Now I'll use some basic quantum mechanics. Okay, so what is the basic quantum mechanics I'll use? So suppose you have, so just for illustration, think of 4 spin half degrees of freedom. Just think of 4 spin half degrees of freedom. You know that if you combine 4 spin half degrees of freedom, then in principle you can have either total spin s equal to 0 or total spin s equal to 1 or total spin s equal to 2, right? This is standard quantum mechanics. I hope I got that correct, but okay, right, good. Now I define a common null space, which I denote by V. This null space is basically this space. And this null space should have some property. What is that property? The property is the following. I define some projection operators. Okay, I define some projection operators. And let's say those, so remember this problem is on a ring. So what does this projection operator do? You take any neighboring 2 sides, I and I plus 1. And of course, you need to be consistent with periodic boundary conditions as well. So there is a neighbor on the edge as well. Okay, so then basically, if your projection operator hits a singlet on those 2 sides, singlet of 2 spin halves, then it spits out a singlet again. And if your projection operator hits a triplet, these are the only 2 possibilities for 2 spin halves, then it gives you a 0. So this is a bona fide projection operator, okay, in the space of 2 spin halves. And I leave this as an exercise for you. The operator for this guy is just proportional to 1 minus sigma I dot sigma j. These are again Pauli matrices, okay? And all that you need to put here are proper prefactors so that these are projection operators. This is a simple exercise. I just leave this for you. So I want this V, this curly V, to be a common null space of all these projectors. So what do I mean? That means no matter which neighboring bond I hit my projector on, it should give me 0. Okay, that's the property I want. So you can ask from quantum mechanics, is there such a possibility? The answer is very simple. If it's not immediately obvious to you, just go back and think for this 4 spin example I told you about. For the 4 spin example, the answer is S is equal to 2. So you literally, so S being the total spin, okay? So you literally just construct all the states for the 4 spin half problem, and you literally construct these projectors, and you literally verify this. Okay, you should be able to show that the largest spin sector, the highest spin sector, with an even number of spins satisfy this property. So of course, if you have L spins, then the largest spin sector is capital L by 2. And what are the number of states here? The number of states here is L plus 1. The number of states here is L plus 1. Okay. So all these L plus 1 states are annihilated by these projectors. But you see, these projectors are local. That's very important. Remember in my first lecture, I was telling you that if you want to write a projector for an eigenfunction, that is a non-local projector. But these projectors are all local projectors. They are just 2 spin objects, right? On neighboring sides. They are local. Okay, good. So let's move on. That is why I made this cryptic remark that this thing can only be order L cross order L or smaller. This is a statement from group theory, but I won't have the time to explain that. Okay. Yeah. Good. Okay, here is a brief explanation, but you can read that later. Now let me define a toy problem and add a perturbation. This is my toy problem. I just do a summation of I sigma I x. This is very simple. You all know how to solve this, and this problem will give you a space like this, right? Okay, and of course we know how to solve this, right? And inside the highest multiplet of S equal to L by 2, there will be L plus 1 states, and these L plus 1 states will be equally spaced in energy. And the spacing would be omega, related to omega, right? That's trivial, okay? Now, let me add a perturbation here, which is an interacting term. Okay, let me add a perturbation. Okay, now let me have your attention for a bit. Okay, this is a bit subtle, but not very subtle. I want to add a perturbation which breaks all these symmetries because I want to do this. But that perturbation should have the property that it should annihilate this subspace. What is that subspace? That subspace is spanned by the 2L plus 1 states of the highest spin representation. Yeah, that's that subspace. Okay, right. So yeah, so you can convince yourself that any term like this does the job. So let me just tell you. So you take the singlet here. Now you take any spin interaction term here, where the sites involved are I minus 1 and I plus 2. They don't change the argument about the singlet because spins at different sites commute with each other. So here the sites are I and I plus 1. As long as the sites here are anything different from I and I plus 1, my argument goes through. I take I minus 1 and I plus 2 because I want to show you the most local example. Okay? And then I just add a summation of I to restore translation symmetry. Okay? Good. Because I want an extensive operator. Okay? And now you can easily show that this operator, and you can take any general spin interaction here. Okay, so I encourage you to think about it if it's not immediately clear. This interaction is very complicated. It's very complicated. This interaction does not commute with this thing. It does not commute with the P singlet of the other thing. So it breaks all the conservation laws. But this entire interaction still annihilates your subspace V. It still annihilates your subspace V. Why? Because of the precise way I wrote out this term. Okay, because of the precise way I wrote out this term. But this is a local perturbation. Okay, good. Yeah. So then what happens is exactly this. For the rest of the space, ETH is restored. But for the subspace B, ETH is not restored. And they survive as quantum scars. They survive as quantum scars. In fact, they are just the components of this giant spin. And now you can appreciate how quantum scars can happen. Suppose I start from a high energy state where the spins are arranged such that the total spin is again L by 2, but the total SZ is capital L by 2. Okay, that spin would of course do perfect periodic oscillations. Why? Because sorry, where did I go? Sorry. Because this term would annihilate that subspace. Only this term would be important. But this term just introduces a precession because your initial state is not in the direction of your magnetic field. That's it. Just like we saw in our integrable models class, right? And therefore, you would have perfect revivals of the wave function itself. So this is an exact Krylov space in the spectrum of an interacting theory. So I see that I'm running out of time. Maybe I'll pause here to take some questions, and maybe I'll take 5 or 10 more minutes extra if that's okay. But this is one mechanism where I have shown you an exact model where quantum scars can emerge, where the rest of the high energy subspace has ETH, but this guy does not have ETH. This is of course a toy example. PXP model is much more complicated. We still don't understand the full story, but okay, yeah. So let me pause to have to take any questions or comments.
So Arnab, I mean, with the perturbation, basically this, I mean, all the other sectors mix amongst themselves except this sector.
Correct.
Right, okay.
Correct. Correct. So the perturbation breaks all your solvability, right? But see, the perturbation is very non-generic because somehow the perturbation annihilates this sector. Therefore, I don't care. This sector is protected, right? But the perturbation is not annihilated by the other guys. So then the perturbation just completely mixes the other guys. Okay. But the cool thing is I can write the perturbation as a local term in space.
Okay.
Yeah. That's the non-trivial thing.
And numerically, you can check that you get Wigner levels.
Yeah, this I can check. Of course, I haven't done this exercise, but I'm almost sure this would happen. I mean, yeah. Yeah, this is bound to happen. Yeah, because this term is very complicated. This term is very complicated. Yeah, it's bound to happen.
And the other question is for the PSP model. I mean, there for the if you like, if sorry, I mean for the scarce states, if you just look at total S, is that numerically that's you find it's high?
So you mean the total entanglement entropy?
No, the total spin.
No, but this is difficult, Abhishek, because here spin is not a good quantum number.
Yeah, but you said somehow
no, but
like
this is another
numerically if you compute.
No, Abhishek, so this is a very subtle point. This is an emergent SU2. This emergent SU2 may not have something obvious to do with your bare operators. See, in your original problem, let's go back to the PXP model. Look at the PXP model. The PXP model does not have a simple SZ conservation or a SX conservation or something like that. It does not.
Okay.
It does not have a spin conservation. But so this emergent SU2 is some other property.
Okay, which one hasn't been able to identify, you are saying?
No, you can roughly identify it, but sorry. So I'll actually take, maybe I go to the Jamboard. Hopefully my Jamboard would work.
Or we can discuss later maybe after you.
No, I can give you a short answer. Let me give you a short answer. I think it's good to give the short answer, specifically for the participants as well. You can still see my cursor, right?
Yeah.
So see, in this toy problem, there are no matrix elements in the Hamiltonian here. This is completely block diagonal, right?
Right. Yeah.
So this splitting is exact. That's why I call them approximate scars. But in the PXP model, what you would see is that there will be a structure which emerges like this if you do ED, right? And a structure which emerges like this. But there are some small couplings here, some dots which would emerge here. Okay, some dots, which will be some small numbers. Okay, so these dots. So basically, this scar subspace is not completely insulated from the thermal subspace. Okay, that's why I'm calling them approximate scars. In fact, that is because of these small couplings here. That is why if you look at the blue curve here in the PXP model, ultimately after a long time scale, there will be a decay, which you should be able to estimate from a Fermi golden rule. Okay. But that time scale would be very large because these matrix elements which connect this guy to this guy, these matrix elements would be very small. Yeah. But if you are asking me why are the matrix elements very small in the PXP model, I have no answer to you. Yeah.
Right. Okay. Yeah.
Hi. Actually, very naive question. So you said that in finite dimensional quantum systems, the scars can be reflected in the eigenstates as like some enhanced structures along classical these orbits.
No, not for finite systems, for one body system.
Finite. Finite.
And let me warn you, I know very little about it, but go on.
Okay. No, I wanted to know if you sort of plot this eigenstates of this PXP model.
Very good question. Very good question. Yes. Very good question. So thanks for that question. If you plot the wave function, so I can motivate the answer in a different way. Remember in lecture 1, I said that if you plot the sorry, I heard myself somewhere. Sorry, there was a So in lecture 1, I said that if you take any high energy wave function and just look at the coefficients in the SZ basis, right? So the mod Ci squares in the SZ basis, you would see a very non-sparse structure, right? But for the PXP model, if you just look at those plots and you compare it with the neighboring ETH states, the plots of the CI squares in the SZ basis, of course here I is a sort of a Fox state in the SZ basis, those plots would look completely different from the stars. They'll be much more localized. I hope that answers your question.
You see some sort of like structured thing in that.
There'll be a structure. Yes. A structure would be. Yes.
Okay. Thank you very much. Thank you.
Arnab?
Yeah.
So is it always true that let's say if I starting with a Hamiltonian and I somehow constrain it such that it's not covering the full Hilbert space? So is it always true that the scar will be emergent from there?
No, I didn't quite understand the question.
Okay.
Somehow protected from the rest of the state. Somehow, yeah, somehow protected. There may be multiple mechanisms of that. This is just one possible mechanism. People don't understand all the mechanisms.
Okay. So scar does not necessarily depends on the constraining the Hilbert space.
No. I think I answered this question in response to another question. You don't necessarily need a constrained Hilbert space.
Okay.
Yeah. By the way, here is the answer to your question. This problem that I've defined here, this problem, right? This does not have a constrained Hilbert space. On a ring with sides L, this has 2 raised to the power L states, right? This problem. But this has scars. Of course, this is a very, what should I say? This is a very peculiar problem because I wanted solvability here. So, yeah.
Thanks.
Other questions? If not, then maybe is it okay if I take 5 more minutes to just say a couple of things about this emergent SU2 thing, because I think it'll be helpful for Bhaskwar's tutorial and the other participants who might be interested. Is that okay, Abhishek? Then maybe 5 more minutes.
Okay, yeah.
So let me just rush through it. It should hopefully become clearer in the tutorial because Bhaskar will show the implementation. So basically, in the PXP model, there's a way to sort of see this approximate SU2 spin emerging. Okay, so the way you do that is something which is very reminiscent of people very reminiscent of something called the Langcho's algorithm in exact diagonalization. Okay, so maybe many people are already aware of the Langcho's algorithm. So you take your PXP Hamiltonian and you split it up. Now this is an arbitrary splitting. Okay, this is an arbitrary splitting. So you split it up into H plus plus H minus, such that H plus is the dagger of H minus. Okay. Now, how do I show you that a giant spin is emerging? I would somehow think of these H plus and H minus as ladder operators. Okay. But these are many body things, but I can still think of them as ladder operators if they satisfy the correct algebra. Because the fact that something is SU2 just comes from the algebra. It does not come from what gives the intrinsic spin to that problem, right? It just comes from the algebra. Okay. So yeah. So I just split my Hamiltonian like this because I want to show this giant emergent spin from Z2. So remember what was the Z2 state? So Z2 state, so I have numbered the sides here because the even and odd sides are important here. So the Z2 state is when there is an up spin on the even side and a down spin on the outside, up spin on the even side, down spin on the outside. And the Z2 prime state is the symmetry shifted, like one translated shifted version of that. Okay, good. So now, what is this H plus? Now this I do by hand. H plus is this guy. So the details Bhaskar will surely fill you in during the tutorial. So H plus is some operator like this. So these are sigma plus and sigma minus. But you see this term only lives on the even sides and this term only lives on the odd sides. This term, other term. And H minus is of course the dagger of that. Okay. And if you add them, you get the PXP Hamiltonian. Now you see H minus annihilates Z2 and H plus annihilates Z2 bar. Okay. So basically Z2 you can think of as the maximally down spin, and Z2 bar you can think of as the maximally up spin. And these guys are like the ladder operators. Okay. Now you form this Krylov space of this giant SU2. How do you form this Krylov space? You start with Z2. You act this ladder operator once on Z2. So you have to act H plus because H minus would annihilate it. So you act H plus on this Z2, you get a different state. Then you act H plus twice on Z2, you get a different state. Now you add H plus L on Z2 and you can prove that you go to Z2 prime. So you go from the downspin, maximally downspin to the maximally upspin. And this is a L plus 1 dimensional Krylov-like space. So what do I mean by that? These states are not orthogonal per se. So you need to just orthogonalize them. So that is called, I mean, that's some standard thing which you also do in Langchos. But the non-trivial bit here is in Langchos, you basically do it for the low energy spectrum. Here I'm doing it for the high energy spectrum. That's the non-trivial bit. Okay. And as I said, I'm imagining H plus and H minus as some fictitious raising and lowering operators of a fictitious S equal to L by 2 spin. Okay. And the revivals that I see in the PSP model are precisions of this large spin. So the downspin is, the maximally downspin is like the Z2 guy. And the maximally upspin is like the Z2 prime guy. So this is a partial answer to Abhishek's question. So here is how the spin SU2 emerges here. So you think of these operators, okay? So now you form this L plus 1 cross L plus 1 dimensional Krylov space. And then you just write your PXP Hamiltonian in your L plus 1 dimensional Krylov space. You can always do that, okay, by hand. So I do that by hand. And this is standard stuff. This will be explained later. You get a tridiagonal matrix from this operation. Okay, you get a tridiagonal matrix. And this is also what you get when you do Langchos. Now, this tridiagonal matrix has only a polynomial complexity, even though you are dealing with a high energy state, because this is just a matrix with L plus 1 cross L plus 1 dimension. Now you just diagonalize this matrix and you get L plus 1 eigenstates. Now, this is an approximation, of course, because I'm doing some approximate steps. I'm doing a projection to a L plus 1 space. So these L plus 1 eigenstates may not have anything to do with your actual many-body eigenstates. But miraculously in the PSP model, these crosses, you can see these crosses. I got these crosses from these very simple problem by diagonalizing this L plus 1 cross L plus 1 matrix. These crosses seem to have similar physical properties as the actual many-body scars. Not exactly, of course, the eigenfunctions are different because I'm doing something approximate, but they have very similar properties. So here I'm showing the overlap of the Z2 field with the scar state and the actual many-body eigenstate. So you see, they have very similar properties, right? So basically, they are not exactly the same because the SU2 is only realized exactly approximately. So what does that mean? I'll just say that and I'll finish because I know I'm running out of time. So you remember I defined this H plus and H minus like this. From this, you can define a HZ operator like this, right? Like this from standard SU2 algebra. Now you can ask whether the algebra closes. That's the real question. Now, algebra would close if you again calculate HZ, which is a known quantity, because I told you what these operators are. So I do HZ commutator H plus. If I just get H plus on the right hand side, then the algebra closes. Then this thing is perfect. The Langchos is perfect. Then these red crosses would coincide with the actual many-body eigenstates. Okay, but actually, when you do this thing for the PSP model, you see that there's some other operator here. There's some other operator here. Thankfully, in some precise sense, which I won't have time to get into, you can say that this operator is small. Okay, and that is why this phenomenology survives. Okay, so maybe this is a good point for me to stop, and sorry for going over time, and I can take questions if you want. So this is how the giant spin emerges in the PXP model. Okay, yeah. So this is the point. Yeah. So.
No, I think so. Yeah, maybe it's a good time to stop now.
Yeah, so maybe after Bhaskar's tutorial tonight, maybe tomorrow I'll ask people if they have more questions that might be more appropriate, right? So
right, yeah.
Yeah. Okay.